Hey, hello everyone. My name is Sean, and my talk is about kind of custom hand-rolled crypto I found in the wild, and how you can also make your own crypto terrible if you so desire. So just a quick, who am I? I'm the CTO at DefenseStorm. We're a Seattle-based cybersecurity startup. Send all your logs to us, and we tell you when you get hacked, that sort of thing. I'm also kind of a security researcher, so in January I presented the LastPass phishing attack against LastPass, if you're familiar with that. That was really fun because it was kind of a pixel-perfect phishing attack. That was a lot of fun to do. But I also like to do crypto. It's a hobby of mine. I'm definitely not like a cryptographer or anything. It's just something I kind of enjoy on the side. And that's kind of where this talk came from. So we're always told by security experts and cryptographers, don't roll your own crypto, right? If you ever find yourself typing AES, you're probably doing it wrong. If you're ever using OpenSSL directly, you're probably doing it wrong. You should probably be using something higher level, something that's easy to get right. But it always kind of comes off to me a little dismissive as well. It really kind of seems like a kind of like abstinence-only education, right? Like, don't learn about this. This is kind of for us smart people. Don't learn about this, right? So kind of like, your safe sex classes, don't have sex, you're gonna get pregnant and die, right? And I was always kind of miffed about that, kind of that tone of that whole thing. So don't roll your own crypto. I wanted to see, like, when people actually, roll their own crypto, do they make tons of errors? They make tons of mistakes? So I needed to find a place where I could get lots of custom crypto. It's actually a little hard to find. We need to find lots of hand-rolled crypto, stuff that's using low-level primitives a lot. And I actually found that people are doing a lot of custom authentication. And where they're doing custom authentication is this thing called single sign-on. So let's talk about it. I made a survey of a lot of different single sign-on implementations, but let me first talk about what single sign-on is, just so everybody understands. We're going to log on to some kind of central server, and that central server is going to provide you access to other systems without logging into them directly. So examples, OAuth, right? If you've ever used any kind of OAuth. Facebook Connect, if you've ever logged into a website and then it redirects you to Facebook or to Google or something. It's an example of a single sign-on. SAML is another open standard to build single sign-on. And some benefits, it's really convenient to provide, you don't have to build your own authentication. You can just use this instead. And a huge benefit is there's fewer passwords. Instead of having 50 passwords out there, you just have the one central system. So what's custom single sign-on? So what if you don't want to use all of these great solutions? You don't want to use OAuth and all this stuff. But why wouldn't you want to use it? They can be a little hard to implement. Especially if you just want a few lines of PHP. Like, think if you have like a WordPress website or something and now you want to authenticate to a support help desk ticketing system type thing. You don't really want to have to implement tons of OAuth or anything. So instead, you're just going to give a secret to both parties. One's the auth provider and one's the other one. You're going to combine it with some few pieces of info, maybe a user ID, maybe an email address, and you're going to produce a hash that is going to be seen by both sides. Let's go through an example real quick, and we're going to check to see if it matches. So just kind of a quick thing about OAuth, just to show you like why somebody would want to not implement OAuth, even though it's like the best, most standard solution. It's complicated. We have, the user needs to request to initiate a request, and then needs to go back and forth, and then the application needs to talk to the auth server directly. Like, if you're just running some kind of little website, this is a big security solution, right? It's definitely the right one for almost every use case, but this is why some people tend to not want to do this, or they ask for something easy. Just give me one function to do it. So let's go through an example of what this custom single sign-on looks like. So Alice runs alice.com, which is a super cool website. Monkey's the user on the website, and Bob runs bob.com, which is a help desk website. Okay, so Bob gives Alice a secret. Says, hey, your user's going to need this to sign on to my website. And Alice is like, great, I'll use that. So Monkey will log into alice.com and does whatever that website is. Alice returns any cookies. Now the monkey is logged on to Alice's website, right? It's going to use the website like normal. But now, the monkey wants some support, right? And Alice doesn't want to build a ticketing system, right? So she's bought Bob's. So Alice is going to say, okay, well, I have to log the monkey into Bob's system. So she's going to compute some kind of hash of the secret in the monkey and say, okay, well, actually go to this website, right, which is bob.com/Alice, and that auth parameter is actually the result of the hash, right? And so the monkey's like, sure, I'll go over here. Now he's over at Bob's website, and Bob is actually also has the secret and also has the monkey, and the URL transfers the monkey's user details, and is also going to compute that same thing. And then because they match, they're both the same. Bob's like, great, you're logged into the support website, now you can file tickets, and the monkey can file a support request. Okay, so the good about this, it's really simple. It's like literally just function, very straightforward, hard to get wrong, like from a, does it work perspective. The bad, these implementations are kind of all over the place. They, aren't very well written. There's no standard implementation. There's no like best practice. This is really how you do it. And the ugly, they're really, really insecure, like really bad, really bad. So an example of one of the problems that you might run into with this sort of thing. This is actually how I found out about this whole thing. So I found this fix. So one of the vendors that does this published this fix. They said, hey, there was a serious problem before, and this patch fixes the problem. So this is a function, basically that H function before. You pass a name, an email, and a time, and there's a shared secret outside of this function, and it combines the name, email, and time. It concatenates them into this thing that it's going to hash, right? That's the thing it's going to hash. But then they changed it to have the shared secret in there, and at first I didn't know what it was. I was like, maybe it's an HMAC. So I don't know of any HMAC MD5 known plaintext bugs. That doesn't sound like anything I know about. I wasn't sure what it was. So I looked it up after it was written up by this cool blog post that described it. So this is the plain text that's authenticated. The name concatenated with the email, concatenated with the time in milliseconds. So Sean at DefenseStorm plus time, right? That's actually the same as Sean S concatenated with EAN at defensestorm.com plus time. So when they redirect to the website, the S is this, the S doesn't matter because they're just concatenating the values together, right? There's no delimiters, there's no anything in there. And they decided to, and so the way you could beat this if you had some kind of, email address admin, right? You could maybe sign up with min at whatever the website is, and then change your name to have AD at the end, something like that. So the fix they had was just putting the shared secret as the delimiter between these two things. So Sean plus ABCDEF plus defensestorm.com plus the time is not the same as these two. This fixes the flaw. This is, a little concerning, and I was talking to a few friends of mine about this. Like, why didn't they just decide to use delimiters? Like, why didn't you just put a null byte in between all of those? That seems like a much more sensible solution. But this is what they decided to do. But this is just got the kind of example of the type of flaws that you see. Like, the previous thing didn't look wrong. It wasn't obviously wrong, but when you look at it like this, it's much easier to see like the types of errors. So I had a few goals for the survey. I decided to survey a bunch of implementations. So I wanted to identify and catalog common issues, like which ones does everybody get wrong on all these different implementations. Report on issues and have them fixed so that, if they're using just a bare MD5, that they're going to update it and actually use an HMAC or something. And then recommend them ways to use cryptography better in general. I had some non-goals as well. I wasn't going to deeply inspect every single implementation and find every single bug. I was trying for more quantity over quality. And I wasn't going to just recommend OAuth 2 every single time because that wouldn't be a very exciting talk. And I also wasn't going to say, don't roll your own crypto 500 times. I was hoping to, have something slightly more interesting to say. So basic stats. So I found 21 implementations, mostly just by Google. So help desk and knowledge base software are the people who use this the most, which makes sense because help desks and knowledge bases are almost always used by a website. So you have your website, it's a to-do list or a hot sauce vendor or something, and you want your users to be able to file tickets, or you want to have a knowledge base about how to use your software, right? There was also 2 education platforms. So if your website wanted to offer training about it, you could then use single sign-on to log your users into the education website. So just a spoiler alert, only one implementation was free from every single problem, every single type of problem I found. We'll talk about what those problems are. One implementation created their own cipher, so MD5, I guess, was too good for them. They decided to roll their own cipher, which is cool. We'll talk about that later. So the total user count for all the services is in the millions. This is very, very popular software. Okay, so let's talk about the issues that I tried to identify. No HMAC. So what's an HMAC? So a message authentication code is going to authenticate and validate a message. So the message is, my name is, the monkey, my email is this, that's your message, and the message authentication code is going to authenticate that with a secret key. So why should you use an HMAC? So it's a secure way to actually combine these things, right? It prevents two main types of attacks, length extension attacks and pre-image attacks. We're going to talk about those in a sec. So length extension attacks. So if we designed a basic message authenticator, like we had no idea what we were doing, we would just say, okay, well, let's concatenate the key and the message, right? We have some secret key, just some random number, and then the message, right? So for instance, MD5 is our hash, and our secret key is ABCDEF, and our message is the URL that we're going to authenticate, right, for our single sign-on. So, HTTP, whatever. So this is our resulting URL. That hash is the MD5 sum of those two things. Okay? Should work, right? No worries. So in either of these ways, no matter where you put the key, if the attacker actually knows the output of the hash and the message, the attacker can actually learn enough about the state to add to the end of the message without knowing the key. It can basically try build up the internal state of MD5 and then be able to add to the end of it. So it's not super cheap computationally, but it's not hard either. It's pretty straightforward. So for instance, the way this would work is this is the URL part. So this results in this hash, right? So what we're going to do is we're going to take the admin false part and we're going to just append admin true to it. Like we're just going to make up this single sign-on thing. And because of the length extension attack, we know exactly how to change the hash. And then now this hash is correct and we don't know the secret key. So almost every single custom single sign-on that didn't use an HMAC could be exploited using this method. So, and this bug has hit Flickr, Amazon, CDN, many others. Length extension attacks happen all the time. It really trips people up. And the way to fix that is just use an HMAC. So pre-image attack. So what a pre-image is if you hash a message, it comes out with an output Y. The inverse of H should give you the message back. So pre-image resistance means that the inverse method should be very hard. And then secondary pre-image resistance means that it should be hard to find collisions, basically two messages that have the same hash. Pre-image attacks aren't super important in single sign-on, but I figured I'd cover it because HMACs help prevent those sort of things. Because even if the underlying hash is vulnerable to it, this prevents pre-image attacks. So like MD5 is broken, but as far as we know, HMAC MD5 is still safe. And it can extend the life of your authenticator. But like I said, pre-image attacks aren't super relevant. So this is what an HMAC is, just if you're curious. So we have a key and a message, and we're going to take our hash function, and this is just a secure way to combine it. I have it here hashing the key and then XORing with some padding, but basically this is just the best way to combine a secret and a message together and then generate a message authentication code. Most crypto libraries support something like this. Okay, so what percent of implementations actually use an HMAC? Only 28% of them actually use an HMAC, so almost, 3/4 of them did not use an HMAC. Usually they just used a bare hash function, so they were vulnerable to some kind of length extension attack. And in my study, if you failed to use an HMAC, you also failed to use a good cipher, so almost certainly you used MD5, and MD5 is really, really trivial for length extension attacks. So using obsolete crypto primitives was another thing I studied. So did you use MD5 or SHA-1? Without an HMAC, they're very, very weak. And there's really no excuse for using bare MD5 anymore. Some of these were written in 2013, like was when they were actually written. We knew MD5 was bad then. So I just defined best practice ciphers. You can use AES, SHA-256, SHA-3. Nobody used SHA-3. That would have been cool. So what percent actually used a best practice cipher? So only 19% use something other than MD5 or SHA-1. Almost always they use that, or somebody wrote their own. This was a little disappointing to me. I was hoping to see more SHA-256 out there. And there was nothing that was really, besides the one custom one, there was nothing really interesting out there. Somebody doing skein or something kind of cool. So short keys. So one thing to note is that from this earlier example, get bytes actually probably doesn't do what you think it does. So shared secret is just a bunch of hex digits. So it's like a 128-bit hex number. But what get bytes does is it actually decodes it into like ASCII or UTF-8, right? So for instance, if this is your secret key, right, this is a hex number. It's a 32-byte string. So what you want to do is you want to do hex.decode hex of the string, right, which is going to return you 0xAA, BB, and it returns you 16 bytes or 128 bits. String.getBytes actually returns you the ASCII values of this, so 41, 41, 41, 42, 40, and that's a 32 length string array. And so if your method is expecting 16 bytes for key, which some of these methods did, it actually truncates it, right? So you only use A's and you get none of the B's, right? And since there's only 16 possible values for each character, because they're hex, you've actually drastically reduced the number of possible combinations. So let's do the math. So the normal secrets are 128 bits. So now the new secrets are only 16 choices per hex character. Each character consumes 8 bits. So 128 divided by 8 is 16, which is what we expect. We expect half. So there's actually 16 to the 16 choices. So 2 to the 128 is this huge number. And 16 to the 16 is this much smaller number. And so it's actually 2 to the 64. And I did the math. This is many nines fewer choices. This is like almost nothing. This is a huge reduction in the number of possible choices. So what percent actually made this error? Actually, a third of them actually made this sort of error. And it wasn't just in Java. People made this mistake in Ruby. But this isn't always a critical bug, because if you actually put the full 32-byte string into an HMAC, it's not... They could hash the whole thing, and it should be still the 128 bits. Some of the implementations had truncation, some of them didn't. But it's definitely sloppy. It's definitely a sloppy way to program crypto. Replay attacks, since these URLs are actually being given to users, and then the browser is doing the redirect, you can't trust the users. They might hold on to that. It might be leaking, right? Some attacker might get that. It's critical they have some kind of time component or something like that. So this is really easy to do. This is what AWS authentication does. They had the timestamp on the end, and they just check to make sure that when they receive the request, the time is recent, within a few seconds. You could use a nonce, which is a number that you only use once. It's a little harder because you have to, check those and ensure that they're only used once. Otherwise, users can just remember and then log in forever. So the percent that kept their hash the same each time, this is actually really good. Most people figured this out, so only a few implementations had static hashes that were the same every time. I was pretty happy about that. Most people had some kind of time component, which means that they were thinking about it. They were really thinking about what would happen if these were being reused. So static initialization vector is another common problem. So instead of hashing it, you could just encrypt the text with a shared key. So instead of doing some kind of hash, you're just going to encrypt it, like for instance using AES. This mode requires an initialization vector, which is usually just some kind of random number. But reusing the IV leaks information in CBC mode. It kind of starts looking like electronic codebase mode, electronic codebook mode. When reusing the IV, right? The CTR mode is another mode of AES that IV reuse is really, really critically bad for. So only one implementation actually used a block cipher, and it was AES 128. And unfortunately, they messed it up. So the only ones, 100% of the people that use a static IV messed it up, and it was OpenSSL for Ruby was always their initialization vector, which unfortunately is just kind of sometimes how Ruby rolls, right? Like convention over configuration, right? So they must have written it in Ruby, kept it the same, didn't realize they had to set their IV. Known plaintext. So in crypto, it's usually best to limit what your attacker knows, like secret keys. Best not to tell your attackers what your secret keys are. The internal state of your crypto function sounds good, right? You probably shouldn't tell them. And plaintext, if you can avoid it, right? You should, it's nice for your attackers not to know what the plaintext is. So knowing or controlling the plaintext makes some attacks possible, right? This isn't always a critical thing. Really well-designed crypto systems can actually withstand attackers knowing or controlling plaintexts. But if you're not using an HMAC, this is actually a really bad sign. So what percentage of attackers know the plain text? Actually, most implementations didn't have a problem with this. They had some kind of hidden component in there.
Hi folks, I'm Geek here. Unfortunately, Avamia seems to have frozen up, so we lose audio till about the 22-minute, 51-second mark. Sorry for the inconvenience.
Base 36 value, and I base 36 decode it into a number, so 145, and then I subtract those two, so 145 minus 48 is 97, and then I ASCII, and then I get literally the ASCII value of the key out. So this actually prints you from one iteration of the plain text and the ciphertext, you get the key. So here's the function. The ciphertext is always twice the length of the plain text, just because that's what the base 36 does. And so for every single character in the plain text, we're just going to get the base 36 value. That just takes two of them and then unreverses it. We're going to unbase 36 it, and then we're going to subtract the magical subtract function that undoes addition. And then we return the key. That's it. So what went wrong with this? So the ciphertext is strongly non-random. The first time I saw this without even looking at the code, I was just like, that's a lot of 4s. That is way more 4s than I would expect. Each input character always results in 2 output characters, which also kind of, from just a ciphertext point of view, just like kind of piqued my interest. I was like, huh, that's weird. The key stream has a very short period, obviously. There's no key schedule at all. They use ASCII values of the key rather than hex values. It doesn't use an HMAC, use base 36. Like, it's almost like I actually had 20 more things to put on the slide, and that was just too many more things. The other thing I wanted to talk about is there's no avalanche effect here. So each input bit should affect all of the output bits. So for instance, if we just change the first input bit, we then only change one value of the output, so it's very easy to see what affects what. Ideally, each bit of change in the input has a 50% chance of changing each output bit. So this would be like the ideal cipher, right? They look nothing alike. They're completely different. So what went wrong? Basically everything. Basically every possible thing that could go wrong. It's not really. This isn't really crypto. This is like somebody doing something for fun. So implications for this application. This is a real application with like actual users. So one attacker can, with one use of SSO, get the shared secret key. So you sign up for Alice's service. You're the attacker. You log into Bob's thing. You get the key. Now you can log in as the admin and see everybody's secret key. You can see everybody's support tickets. You can see everything like that. The authenticator can authenticate as anybody. So it's this is a privilege escalation attack just done over single sign-on, right, with this kind of crappy function. So I think from all of this, we really have enough evidence to say, no, you shouldn't roll your own crypto. It's actually pretty hard. People make mistakes all over the place. So just talking about overall results, these are like the kind of the each category and the number of implementations out of 21 that had the problem. So a lot of people had no HMAC. A lot of people used obsolete primitives. We had the one custom cipher. I actually had to add that category during the study because I didn't expect anybody would do that. I thought more people would use AES than, that's why we only got the one static IV. And so the vendor response. So only one vendor fixed the bugs that I reported out of the 20 that had bugs. And it was User Echo, which is customer service software. So go them. They didn't use an HMAC, and they did it. And they were actually super responsive, so good on them. 2 claimed that they weren't bugs, and these were some of the worst implementations, too. These were not like the barely, the HMAC MD5, which actually, HMAC MD5 is not that big of a deal. About half of them never acknowledged, even replied to my email. Some of them were, to be fair, like unsupported optional plugins. You didn't have to use them, so they said they weren't a priority to fix, which, fine. But I just, you have to think about this kind of stuff. And this is the sort of stuff you don't really think about when you might be evaluating, support software. You might not be thinking about, like, oh, well, there's these crypto problems, right? So here's just a pie chart of all those things. Definitely a little disappointed. I was hoping to get some more fixes in there. And especially because some of these have millions and millions of users. Some big ones like desk.com are not in this, and you notice I didn't, name drop anybody, but so desk.com doesn't have custom authentication in here, so like they're not in here, but there are some big players in here. So custom single sign-on the right way. First, you really need to decide if you actually want to do something like this, because OAuth 2 and SAML, they're really, really much better choices. They do, you can give partial permissions. It's a standard. It uses good crypto. There's great implementations of it. It's actually not that hard to use. But let's say you can't. Let's say a core use case is supporting WordPress things, right? You really need to closely examine why. Can you get maybe you can write a better integration with your product that uses OAuth simpler, but okay, because this is really a very important part of your application. Authentication is critical. If you just let anybody in, anybody's going to be able to use your, anybody's going to be able to privilege escalate or do something else, right? So, okay, if you must have it, I recommend you do something like this. Use an HMAC, preferably with SHA-256 or SHA-3. SHA-3 actually, interestingly, isn't vulnerable to something like length extension attacks because it doesn't use the Merkle dam guard construction. It's actually based on AES because it's Ketchek. 256 bits of secret sounds good to me. Generate this using dev-view-random. I actually had an argument with a friend of mine about dev-random versus dev-view-random. No difference anymore. Just use dev-view-random. It doesn't block. Dev-random doesn't do anything with really it just blocks and it just makes your application annoying. So dev-view-random is totally fine. Use that. Really triple check to make sure you're actually using all of the bits that you generated. Even if you're only using half, 128 bits, pretty good, but make sure you're actually decoding your hex and actually not getting the ASCII values. That's just sloppy. Hash several pieces of data, including some the user doesn't control, like maybe a user ID, something like that they can't pick, or maybe they don't know. Use a non-cert timestamp and actually check the non-cert timestamp. There was actually one implementation that didn't check the timestamp, even though they had it, which, whoops. Rate limiting requests is always good. This stops practical attacks. And having a security consultant or a security consultancy actually review your implementation code is always good when you're doing some kind of custom authentication, especially with crypto written by non-experts. I just wanted to go through other dumb ideas for your crypto, because this is the kind of stuff that annoys me. So using really weird block cipher modes like Telegram's IGE mode, literally the only people who use IGE, as far as I can tell, is Telegram. They're like a messaging app that does kind of questionable things with their crypto. Other things to do, don't make impossible to win contests. Like, crypto is pretty hard. If anybody's ever done a crypto CTF, like, they're actually pretty challenging even when they're meant to be solved. And so if you create like an impossible to win contest, it doesn't really impress people who know what they're doing, right? So if I just say, oh, I have this custom crypto cipher and it's sending it to this computer over here, and you don't know anything about it, most people aren't going to just, spend 6 months of their life trying to win your contest. Telegram did this. You guys can tell probably that I'm not a huge fan, but they made a contest that was just one user talking to another user, and they basically said, yeah, if you can decrypt it, we'll give you, $100,000, which isn't how a lot of crypto fails, right? Crypto fails in side channel attacks or partial key reconstruction. All these interesting things that were completely ignored by this contest. There was another thing that I found, 1,000,000-bit encryption. So it was military grade and bank trusted, and essentially what they were doing is just a one-time pad. They would just generate huge 1,000,000-bit random number generators, and they're like, this is uncrackable. That's all crap. Don't do that. Using a bad random number generator is a really great way to ruin crypto. And making your crypto really hard to get right. So like this is like OpenSSL. Like OpenSSL is tough. If anybody's ever used OpenSSL, the actual option to make it verify SSL certificates is true. So if you pass in, it's 2. So if you pass in the constant true, which is defined as 1 NC, it doesn't verify SSL certs. Whoops. So like that's annoying, and just stuff like that. You just really make your crypto really easy to get right. So stuff that I really like is like libsodium and NaCl from DJ Bernstein, that kind of stuff. It's much higher level type things. That's really it's really nice. And ignoring everything everybody else has learned about crypto is a really good way to make your crypto suck. So in my opinion, I think absence-only crypto education doesn't work. Because I wanted to examine why these companies made these mistakes, right? So, and I don't think it's because they're dumb. They're smart people there. This is good software, right? And they don't want to make insecure products. And I don't even think it's that they're incompetent. I think the problem is that they're not cryptographers, right? And I don't think they should have to be. I don't think you should have to be a cryptographer or security expert to make this software secure. I think all of us, have kind of actually let them down, right? We sort of shame people who are trying to learn crypto. Even I sort of did it in this talk because it was fun, right? We discourage any solution but the standard, right? It's either OAuth or bust. But really, sometimes they are too complex, and that's obvious because I found 21 custom implementations. That's 21 reasons why OAuth is too complex, right? It's too complex for some category of user. And I think there really needs to be simple, copyable crypto solutions for these cases. This is obviously a common problem, so people should have the right solution to crib off of. I also think we need crypto APIs that are really hard to use wrong. Really, OpenSSL is kind of the best, the most widely used crypto API, and it really, really is hard to use. And I think we should encourage people to learn crypto. I think it should be.
Unfortunately, we had another freeze up, and we don't have audio for the rest of this video. I'm sorry.